and who did all the implementation. Also, before I start, like Joaquin, I also like questions, so feel free to ask. So yeah, where do we start? We have seen these kinds of graphs before. So we start with a simple state space model. So we have a Markov chain X, which models some phenomenon in which we're interested in, but which we cannot observe because at each time point we only observe some observation y. Yeah, and densities, and okay, if you believe me when I say that there are plenty of applications of these in many different fields. For this talk, I will assume that we have collected capital T observations, and also that our latent states are capital D dimensional. Yeah, so that means that the joint posterior distribution of all the states, given all the observations, the joint smoothing distribution is T times D dimensional. Yeah, and specifically in this talk, I will assume that this has a, well, that this joint smoothing distribution has a continuous density and everything is nicely differentiable, yeah, because we'll be calculating gradients later. Yeah, so the goal is then, my goal for this talk is to construct or to find efficient MCMC algorithms which allow us to approximate this joint smoothing distribution. And if either D or T or both are large, then this will be challenging. Yeah? And so we need some more sophisticated methods. Yeah. So just for this talk, I'll need a bit more generic notation. So I will assume that I can write my joint smoothing distribution in this form. So it factorizes into a product of mutation kernels and potential functions. And again, I'm assuming that all of these are sort of continuous and differentiable and all of that stuff. And we will also sometimes need the filters, which is really just the same thing as the, my notation, the same thing as the joint smoothing distribution, except up to sometime little t rather than capital T. Yeah, but if we are interested in state space models, yeah, where this distribution, this joint smoothing distribution by t is a posterior distribution, then we can recover that by setting the mutation kernels to be the transition densities of the state space model and the potential functions to be the observation densities. Although I should say that is not a unique representation. You can find other ways of representing a state space model as such a generic Feynman-Carr model. Okay, so there are sort of three methods that I want to talk to you about that exist for dealing with this problem. And the first one is classical MCMC. Now, what do I mean by classical MCMC? I really just mean MCMC methods which are agnostic to the state space model structure. Yeah, so that means for the moment, I would just drop all the time subscripts because the MCMC methods I'm going to talk about, they are not aware that we have this state space model structure. Yeah, so in this case, our problem is simply a distribution pi, which is proportional to some prior m and some potential function, meaning likelihood g. Yeah, and again, x might be high dimensional, yeah, because it's t times d dimensional. Right, so this one you all know, so the simplest kind of MCMC algorithm is the Metropolis-Hastings algorithm, where you propose some state from a proposal Q, and then you accept that with some suitable property. I'm calling that the marginal sampler here, which is non-standard, but there's reason for it because I'll show you an alternative auxiliary sampler in just a second. And this auxiliary sampler will rely on the fact that we can often represent this proposal distribution of the Metropolis-Hastings algorithm as a marginal of some extended proposal where we're introducing some auxiliary variable u into the space. Yeah, and so then with this, we can construct what I'm calling the auxiliary sampler, where we first propose this auxiliary variable u, and then we propose a state x tilde, and then we again accept or reject that with some suitable probability. The only important thing is now this acceptance probability will depend on this auxiliary variable u. And there are many, these sort of auxiliary samplers have appeared many times in literature, and they have at least two very nice interpretations. So the first one is, oh, I should have been able to uncover only one, but let's focus on the first one first here. So the first one is that if you condition on the auxiliary variable u, so given the auxiliary variable u, this is really just a standard Metropolis-Hastings algorithm targeting a distribution which is indexed by you, and also using a proposal which depends on you. Yeah, so given you, we just have a standard Metropolis-Hastings update. The second interpretation is also nice, which says that if you look at this representation of the acceptance probability here, actually this is not quite correct, because this should just be the acceptance ratio and not the acceptance probability, I think. But essentially what the second interpretation says is that you're accepting the new state with using some acceptance ratio, which is just a noisy version of the acceptance ratio in the Metropolis-Hastings algorithm. Yeah, and then this interpretation is nice because you can then show, and there's this paper by Christophe Andrieux and Marty, that because you're essentially doing a Metropolis-Hastings algorithm with a noisy acceptance ratio, this auxiliary sampler cannot be better than the marginal sampler. Yeah, so for the moment, there doesn't seem to be any reason for doing this, but it will give us some nice algorithms later on. So that's why I'm introducing this auxiliary variable process. Okay, so let's look at some examples of very simple Metropolis-Hastings algorithms. Yeah, so you all know this one, independent Metropolis-Hastings algorithm we just proposed from the prior. And okay, here is a slide that I will keep showing you throughout this talk. So what do we have here? Here I will show you a simple linear Gaussian state space model. Yeah, so with transition densities like this and observation densities like this with 25 time points. And what you see here is the mean square jumping distance, which is kind of a measure of how well the algorithm works, how well it scales. Yeah, we want this to be high. And in particular, I'm showing you the results here for a particular state dimension D. And what we would want here is to have a horizontal line, because that effectively means that in order to stably approximate marginals of my joint smoothing distribution, I would only need to grow the number of MCMC iterations linearly in D, which is kind of the best thing I can hope for without assuming additional structure about the space. Yeah, okay, so I've told you now how to interpret this, but you don't actually see anything, which is as intended because we know that independent Metropolis-Hastings algorithms don't really work in high dimensions. Yeah, and even for D equal to 1 here, our problem is already 25 dimensional. Yeah, so you don't see anything because this algorithm really doesn't work. Okay. And let's try something better. So I'll show you some that actually do work in just a second. Yeah, so we know from lots of literature that what we can do and should do in this case instead is, rather than trying to propose global moves, which almost always end up in the wrong place, we should just try to move locally. Because once we're in the right part of the space, proposing a local move means we stay in the right part. Yeah, and that means we are likely to accept such a local move. Yeah, so the simplest algorithm is the random walk Metropolis-Hastings algorithm, where we just propose locally around our current state using some using some step size parameter delta. Interestingly, so I told you about the marginal sampler and the auxiliary sampler earlier. Interestingly, we can construct a similar auxiliary sampler for this algorithm as well, because we could sample from this random walk Metropolis-Hastings proposal kernel by first sampling an auxiliary variable u in this form and then proposing a new state in this form. Yeah, so there is an auxiliary sampler for this one. And now, in this case, the auxiliary sampler is not very interesting because it's statistically equivalent to the marginal sampler. Yeah, because the auxiliary variable u will just cancel out in the acceptance ratio. Yeah, so for the moment, the auxiliary sampler in this case is not interesting. Yeah, but in principle, we could interpret the algorithm as an auxiliary sampler as well. Okay, so how does this look like? Well, so now in our picture here, we see that we get some kind of stable behavior with dimension. Yeah, so we know that if we grow the number of iterations linearly with a dimension, with D, then we can stably approximate fixed dimensional marginals of our. Yeah, so that already is progress. Now we can do better because we could try to exploit gradient information. Yeah, using information about from the gradient of our target distribution, and that gives you the Mahler algorithm. No, sorry, the Mahler. The last A is already on. So yeah, so that is the Mahler, which is, well, the proposal is the same as the random walk metropolis, except that you have this extra gradient term. And again, you can construct an auxiliary sampler of this form, yeah, where you sample the auxiliary variable first, and then you propose your state. Now, in this case, the auxiliary variable U does not cancel out the acceptance ratio. Yeah, so the auxiliary sampler is not statistically equivalent to the marginal sampler. Yeah, the auxiliary sampler I'm calling, well, is called auxiliary Mahler here. Yeah, just interesting that we can construct such an. Okay, and here is what this looks like. Yeah, so we do a bit better. Now, for you, those of you who know that about this stuff, they will be wondering why this line is decreasing, or at least not increasing. Well, normally we would know that Mahler works should scale much better with dimension than the random walk metropolis algorithm. Doesn't happen here, but that's probably just because A, we didn't really tune this, and Mahler is known to be really, really sensitive to tuning, and B, we probably should have done some preconditioning here, because we have a complicated structure of our target distribution, yeah, because this is still a state space model. So probably that's why it doesn't look so good. Okay, next one. So now we can use gradient information, but we can do even better. If we have a Gaussian prior, we could try to use information from that as well. And that's sort of motivated by the idea that if your likelihood is really uninformative, then you wouldn't want to do local moves. You would just want to sample IID from the prior, right? So, and if you have a Gaussian prior, we can do that. Now, so then there are algorithms which try to sort of combine both ideas, and one of them is this Quark-Nicholson-Langevin algorithm. And without discussing this in too much detail, if you just look at the proposal mean here, you can see that if you look at beta here, it's kind of a mixture between the prior mean and a sort of gradient type local move. Yeah, so that it tries to combine both of these ideas in some way, which I don't want to discuss any more than that. Yeah, and again, you can construct an auxiliary sampler. Now, there's an algorithm which does something similar, but actually seems to work much, much better. So that's why that's the one I'll be looking at in the rest of this talk. And that's the marginal gradient sampler from this paper by Michaelis Titsias and Omeros Papaspilopoulos. And again, if you look at the proposal mean, just at the mean, you see that again, if A is essentially a matrix of zeros, then you do you propose with the mean equal to the prior mean. But if A is the identity matrix, then you essentially have the mean of the Mahler proposal. Yeah, so again, this algorithm combines both prior information and gradient information. And again, we can construct an auxiliary sample of this, which is called the auxiliary gradient algorithm.
Sorry,
okay.
What is A again? Is that up to you to construct that matrix, or where does it?
No, A is defined by it depends on so C is the prior variance. So actually A will scale in a suitable way depending on the prior variance, which I'll come to at the end of the talk. So it's actually even more interesting than just some fixed A. I don't even need to, in some sense, it automatically tunes itself to how informative the prior is about the target distribution. But I'll come to that at the end. Yeah, and so this algorithm works really, really well. Okay, so now you might think, okay, A, haven't we just solved the problem? Because I've shown you a slide which I think seem to work really well. And B, this is an SMC workshop. I've just shown you a bunch of MCMC algorithms. Yeah. So yes, that's true. These methods work really well, and they can use gradient information and Gaussian prior information and local moves. But the problem is that they are agnostic to the structure, to the state space model structure, to the decorrelation over time property of my target distribution. And therefore, they don't scale as well with the time horizon t as they could. Yeah, so if we look at, so this is now the same model, but now I'm fixing the state dimension d, and I'm just drawing the time horizon t here. And on the second axis now I'm dividing the mean square jumping distance by t. So if you have a horizontal line here, it would mean that you can keep the number of MCMC iterations fixed in the time horizon, which for none of these MCMC algorithms we can do. Yeah, again, because they don't exploit this, the model structure really. So that's where maybe we can do better. And we can do better by using conditional sequential Monte Carlo methods. So what's the CSMC algorithm? For the moment, I'm just assuming that t is fixed and small. So that's some complicated method that again gives you a pi t invariant MCMC. And it does that in a complicated way using n+1 samples. So this is important in this talk. The total number of particles that I have is not n, but n+1. And it sequentially builds up a proposal in the time direction, this sort of high-level way in which we highlight this. This is the algorithm. There's a lot of stuff going on here. None of that, or most of that, is not really important for this talk. The main bit here is we are given some existing state x in red. We generate lots of particles. The particle with index 0 is set to the current state. That's called the reference path. And then we do some magic, and then we get a new state out at the end in blue. And what this magic is, I'll try to show you in pictures rather than mathematically, because it's much. So here's the current reference path. So that's the current state of my Markov chain. Yeah. And what we do is we set one particle, the particle with index 0, to the component of the current state. And then you propose lots of particles from the first mutation kernel. Yeah, so now you see some of those particles are in the right part of the space, and some are maybe in a part of the space where they shouldn't be. So they get killed off. That's our resampling operation, right? And only the other ones propagate to the next time step. Yeah, and then again, we have again proposed particles from the mutation kernel. Again, some of them have low weights, they get killed off, and the others propagate, and so on. Yeah, and then we're left with this sort of genealogical tree construction. Now, how do we get a new state? Right? We're still trying to do some kind of MCMC update. Yeah, so how do we get a new state, a new sample from my posterior distribution? Well, you pick one particle at the end. This one, let's say, with some suitable probability. It's not important here. And then you trace back the ancestral lineage. And that's the new state of my Markov chain. So far, this all looks good, right? It looks like I've updated all the entire state sequence.
Wouldn't this suffer from path degeneracy over?
Yeah, that's what I'm coming to now. So this all looks good. I've updated all the states, but I'll come to that in 1 second. Yeah, so this way we induce an invariant MCMC kernel, and the key thing here to see is that we essentially do T accept reject with decisions rather than one as we would in a classical MCMC algorithm. That's sort of my high level view of these things, and I'll show you this now. Again, what you alluded to. So it could also happen. So in the former case, essentially I accept it at all t time points. Yeah. But it could also happen that I maybe pick this particle at the end, and now when I trace back its ancestral lineage, I have essentially accepted moves at the last 2 time points, but I've rejected moves at the first 3 time points. Yeah, because the lineages coalesce with the original state sequence, with my original reference path, and so nothing moves here, right? So this part of my state sequence is not updated. Yeah, and so there are results that we know we need to scale the number of particles to basically control this problem. Now, for the rest of the talk, I will introduce 2 extensions of the conditional SMC algorithm. The first one is now what you see in point 2 here. Don't worry so much about this. It's just a slight modification, which essentially means that I slightly reduce the probability of picking this particle at the end here, but it's not really important. But for those of you who might be curious, it's essentially the difference between, well, it really is the difference between using the Metropolis acceptance probability versus Barker's acceptance probability. Yeah, but it's not really important. The bigger important aspect is that in the last step here, where I'm picking my new reference path, I'm just going to do backward sampling now. And so that helps us with this degeneracy problem, which we just saw. Yeah, backward sampling, essentially what it does is it allows you to pick a new reference path, which is not restricted to the existing particle lineages. Yeah. But as you see here, you can still reject, right? So in some sense, we do a rejection at this time point. Yeah, at this time point, at this time step, we get out the same state that we put in. Yeah, and so if you look at my scaling with the time horizon, now you see this algorithm exploits the property, the correlation over time property of the target distribution, and so we get much better scaling with time. Now, what happens in high dimensions, where by dimension I now mean the state dimension. So this is my visual representation of higher dimension. Yeah, the target becomes more concentrated in some sense. But then in high dimensions, what happens is that as with the independent Metropolis Hastings algorithm, it's incredibly difficult to propose particles in the right part of the space. So they all get essentially killed off at each time step. Yeah, and so when you try to select a new particle lineage at the end, you just get out what you have put in. Yeah, so basically your algorithm, your Markov chain gets stuck. You never accept any moves at any point. So all the acceptance rate go to 0, and this even happens if you use backward sampling. So that doesn't save you in this. Yeah, and so here it's the scaling with the dimension. So you see very quickly the mean square jumping distance for the conditional SMC algorithm just crashes. Okay, so in summary, conditional SMC algorithm works well or scales well with the time horizon t, but doesn't scale so well with the state dimension d. Yeah, and the reason it doesn't is because it cannot use local moves. It tries to do global moves at each time point. So let's try to change that. And so there's an algorithm that is from a paper that we wrote a while back, which I'm calling the particle random-walk Metropolis algorithm here. And so it looks similar as the conditional SMC algorithm. That's why I haven't given you all the steps here. The main change is that now my particles are proposed differently. They're not sampled from the mutation kernel, but they're sampled in some suitable way locally around the reference path, in such a way that marginally, if I just look at the proposal of an individual particle, it is sampled from this distribution, which is exactly the proposal of a Gaussian random-walk Metropolis algorithm. Yeah. So they're all sampled. They're not independently or conditionally independently sampled, but marginally we get the Gaussian random-walk Metropolis proposal. So yeah, and it turns out that you can then scale the step size in essentially the same way as in the random-walk algorithm. You get a stable algorithm. Yeah, so what does this look like? So now I'm just placing my particles locally around the reference path. And so in high dimensions, I would just place them closer and closer to the reference path. Yeah. And that effectively stabilizes the genealogical tree. Yeah, so even in high dimensions, I still get a new lineage out. Yeah, my Markov chain doesn't get stuck. As I'm using local moves here. And so, okay, let's again look at the scaling with the time horizon t. Everything still looks fine. Maybe not quite as good as conditional SMC algorithm here, because maybe the dimension is not high enough. But now if we look at the scaling with the state dimension, where the conditional SMC algorithm, remember, that crashed here, and now we get something that looks stable. Yeah, and so one really nice interpretation from Adrian's paper is that you can interpret this algorithm as really So it's again, you can interpret it as an auxiliary sampler again, in the sense that you can, that conditional on having introduced all these auxiliary variables u, it becomes just a standard conditional SMC algorithm with targeting a slightly modified model. Okay, so in summary, we have introduced, or we have looked at the particle random walk metropolis algorithm, which seems to scale favorable with D and seems to be stable in D, but it does not use gradient information or prior information. As if I had a model in which the prior was really, really highly informative, I would probably want to use a conditional SMC algorithm instead, rather than trying local moves. And so in this talk, basically, I will introduce methodology which fixes both, which extends this methodology to use gradient information and also potentially prior information. Yeah, so let's first utilize gradients. So the first algorithm that we introduce, we're calling particle Muller. And okay, it samples particles again in a complicated way using an auxiliary variable here. But the main thing is that marginally, the nth particle is proposed from this distribution, which looks like the Muller proposal. Right? So in particular, we are now using gradient information here, information about from the filter gradients to be more precise. I should point out here, I'm not telling you what the weight update looks like. I'm not telling you what F is, but interestingly, in this algorithm, the weight of the nth particle depends on the values of all other particles, yeah, but only through a sufficient statistic. So the algorithm, the cost still scales linearly with the number of particles. And yeah, so it turns out that this algorithm reduces exactly to Muller if you have one proposed particle in addition to the reference particle and one time step. Yeah, and then as usual, in this case, in the particle Muller, we're integrating out the auxiliary variable in the weights. But if you don't do that, then you get an algorithm which we call particle A Muller, yeah, which can be viewed as a random weight version of particle Muller, and which then reduces to particle A Muller, the auxiliary Muller in the n and t equal to 1 case. Yeah, and so what does this look like? So again, we inherit the stability in the time horizon. That seems nice. And now in the scaling with the state dimension, well, again, we seem to be doing well. It's slightly concerning that this is a bit decreasing here. I don't know exactly why that is, but our conjecture here is that it's due to the fact that we use gradients with respect to the filters and not gradients with respect to the joint smoothing distribution. So a gradient doesn't take future observations into account effectively. Yeah, and so that's why what we're not now going to fix. So now we're going to use gradients which take future observations into account. Yeah, gradients with respect to my target distribution. Yeah, so again, everything looks a bit complicated here. The details aren't important. Again, the main thing is that we are now proposing particles from a joint distribution, which is such that marginally we again have this Mahler-like proposal, but now the gradient is the gradient with respect to the joint smoothing. Now, this comes at a cost, and the cost is that your model, you're now essentially targeting a model which is no longer first order Markov, but second order Markov. Yeah, and so the weight updates are a bit more complicated. So that's why you get this really nice thing here, which if you ever talk to people who don't like SMC, that's why they don't like it. Yeah, but it's still, the cost is still linear in N and T, but it's a bit more complicated. And again, this reduces to A Muller. Again, with the time horizon, it behaves nice and stably, and then it also seems to scale quite nicely with the state dimension. Okay, so now we have exploited gradient information, but what about prior information? Yeah, so it could still be the case that we have a highly informative prior, in which case we might just be better off sampling from the doing a standard conditional SMC algorithm rather than trying these local moves. So that's what we're going to do now. So for the moment, I'm assuming that my mutation coordinates are Gaussian. Yeah, but the joint prior is not necessarily Gaussian, yeah, for the moment. Yeah, because the mean might depend non-linearly on the previous state. And in this case, we have another algorithm which we call particle mGRAD. Again, there's some complicated joint proposal going on here. The main thing is that conditional on the auxiliary variables, so we can treat the auxiliary variable as a kind of pseudo observation, and then conditional on these auxiliary variables, we propose particles from a proposal which you can recognize is effectively the fully adapted auxiliary particle filter proposal, if your observations are these pseudo observations. And marginally, this proposal here would propose a particle from this distribution, which is, you probably don't remember, but this looks like the mGRAD proposal here, in the sense that you can view it kind of as a mixture of the prior mean and of a kind of local gradient type proposal, depending on what this matrix A is. Yeah, and indeed it reduces to mGRAD if n and t are equal to 1. And again, we can construct an auxiliary sampler version of this. If we don't integrate out the auxiliary variables in the particle weights, then we get a kind of random weight version, which is slightly nicer in the sense that it is implementable even if the prior covariance matrix depends on the previous state. So we're slightly more flexible there. And that reduces to the mGRAD algorithm, unsurprising. Excellent. Okay, so what does it look like? Again, it seems to inherit this nice stability with the time horizon, and also seems to work quite well with the state dimension. As the state dimension increases, again, slightly concerning that the line is falling here. But well, I will not go into details for this now. Okay, so we can do better, and that is, well, if we assume more structure about our model, so now then we can do better. And what I'm assuming now is that the prior dynamics are not conditionally Gaussian, but unconditionally Gaussian, meaning that the joint prior distribution of all your states is Gaussian, meaning effectively you need a linear Gaussian dynamics. Yeah. So that's what I'm assuming now. So I'm assuming now that we have linear Gaussian prior dynamics. And in this case, we can come up with another algorithm, which we call the twisted particle mGRAD algorithm, which again, there's a lot of stuff going on here. In this case, it's more convenient to sample all the auxiliary variables first. And then we sample in the particle filter, we sample the particles from some mutation kernel M prime here, which now depends on the current and all future auxiliary variables. And what this is really nothing other than the fully twisted particle filter proposal for the pseudo observations UT for my auxiliary variables as pseudo observations. Yeah, so essentially now my algorithm, the proposal utilizes information contained in all the future auxiliary variables. And yeah, let's look at how this works. Again, seems to scale well with the time horizon. And now with the state dimension, it really blows everything out of the water. Yeah, but of course, it also makes the strongest assumption on the model. Interestingly, so it turns out that these mGRAD and mGRAD algorithms, and similarly the particle versions that we have here, they seem to be very robust to sort of tuning requirements, yeah, unlike Mahler. And I want to now give you some results which sort of explain why that is. And effectively, what we're going to see is that the particle mGRAD and mGRAD, they interpolate between conditional SMC and particle Mahler, depending on how informative your prior is. So let's, for simplicity, assume that our mutations are just sort of independent over time and just sort of Gaussians here. And so then, to remind you, the particle mGRAD and aGRAD, they propose particles marginally from a normal distribution with a certain mean and a certain variance. And the mean, again, has this nice interpretation as being some kind of a mixture of the prior mean and of a local gradient type. And it turns out that if your prior is highly informative, so if all the eigenvalues of C are small, yeah, so if the prior variance is really, really small, so then your target distribution is dominated by the prior. And in that case, your mGRAD marginal proposal is just the standard CSMC proposal. Yeah, so if the prior is really informative, these algorithms effectively reduce to the conditional SMC algorithm, which is what you would want. Yeah, if your likelihood is flat, then you would really just want to sample from the prior. And similarly, if your prior is highly uninformative, yeah, so if your prior is really diffuse, then using the conditional SMC algorithm is a really bad idea, yeah, because if your prior is not informative about the target. And then you really want to do some gradient local, you want to do some local moves. And it turns out that if your prior is uninformative in this way, so if all the eigenvalues of C are large, then this proposal here effectively becomes the particle-Muller proposal. Yeah, so these algorithms, they interpolate between the conditional SMC algorithm on the one hand, if your prior is really informative, and between Muller, particle-Muller, and all these types of methods on the other hand, if your prior is uninformative. So here's a picture of what this looks like. So this is again the state space model that I showed you, but now note this lambda here. So that's my prior variance. Yeah, so that if lambda is small, then my prior is really informative. If lambda is large, then my prior is really uninformative. And you see here, if the prior is really informative, so if lambda is small, then particle mGRAD, aGRAD, and the twisted version, they all do the same thing here. They all behave like the conditional SMC algorithm. Yeah, but as the prior variance increases, so as my prior becomes less informative, you see that the conditional SMC algorithm just collapses and just breaks down. And for uninformative priors, suddenly Muller and particle-Muller and all of these methods are good competitors here. Yeah, and in this regime too, particle mGRAD and aGRAD behave similarly to those. Yeah, so it seems like these algorithms more or less tune themselves to the prior, to the informativeness of the prior, which is kind of a nice property to have. Yeah, we can show this more formally. Yeah, so we have results which show that particle mGRAD and aGRAD, they converge to Markov kernels that they induce, converge in total variation distance to the conditional SMC Markov kernels if all the eigenvalues of my prior covariance matrix go to 0. Yeah, and the assumptions here, well, the second assumption is kind of mild. It just says that we have some kind of Gauss condition related to the gradient of the log potential functions. Assumption A1 is stronger. It says that the model factorizes over time, but I'm sure this can be relaxed. And in fact, that assumption actually doesn't hold in this example. Yeah, so I'm quite confident that that can be relaxed. And then similarly, if the eigenvalues of C all covariance matrix all go to infinity, so if the prior becomes really uninformative, then particle mGRAD and aGRAD converge to Muller or absolute. As a sort of picture was drawn. So that's and yeah, of course, these results also then, if t is equal to 1 and n is equal to 1, these results will also apply to the standard mGRAD and standard Muller. So I think this gives a nice intuition for why these methods sort of seem to be robust to sort of tuning requirements. Numerical illustration, just very quickly. I just want to show you some results for a multivariate stochastic volatility model. In this case, we have a parameter tau, which again relates to the prior variance. Yeah, so that controls the informativeness of my prior. And so here, firstly, I'm going to show you the results for those methods which do not make any assumption, like any sort of assumptions about the prior. So, yeah, so these methods here, they don't assume any Gaussianity in the mutation kernels. And we'll see here, so the left panel is the unnormalized effective sample size. The right panel is the effective sample size divided by controlling for computation time, divided by computation time. And well, you see that the particle Mala plus, so that's the one that uses smoothing rather than filtering gradients, works really well. But then when you take computation cost into account, yeah, it's not clear. Yeah, but they still seem to be working much better, or at least somewhat better than the algorithm that doesn't use any gradient information. So now we look at algorithms here, which are the ones that assume Gaussian mutation kernels, but not necessarily linear Gaussian mutation kernels. And yeah, so that's the particle mGRAD and aGRAD. The order is not quite clear here. And also in blue here, you see some algorithms that I haven't really mentioned. So kappa equal to 0 just means I've switched off the gradient in some sense. Just to see if the gradient is really needed. And then finally, so now I'm assuming linear Gaussian dynamics. So then we can implement these twisted algorithm in green here, and that seems to be working much better even when accounting for computation time than the existing aGRAD algorithm, which is down here. I should note there's a dip here in the line, but there seems to have been some computational cost issue with the cluster, I think. Right. So that was my talk. Yeah. So we've introduced methodology which for high dimensional state space model, which borrows from classical MCMC algorithms. It borrows the ability to make local moves based on gradient or Gaussian prior information. And from conditional SMC algorithms, we borrow the ability to exploit sort of the model structure. And that gives us both nice scaling with D and with T. All methods can be implemented across that is sort of linear in N and T for a fixed dimension. And all methods are exact. I haven't really talked about any proofs here, but yeah, you can prove that they all are exact in the usual MCMC sense. Yeah, and so if T is 1, and if you only make one proposal in addition to a reference path, then all of these methods reduce to sort of well-known classical MCMC algorithms. And if T is equal to 1, but you take N greater than 1, then our work sort of as a byproduct gives you multi-proposal versions of Mala or of mGRAD or of aGRAD or of any of these which might be of interest in their own. So that. Thank you.
Thank you, Axel. Any question?